about general aspects of matrices, and a matrix can be 1 minus 1, 0, 2, 3, minus 6, and this matrix, it is a 2 by 3, okay? It's a 2 by 3 matrix, and then we can consider, just for a moment, we can consider the columns of A, okay? So let's assume that the columns of A, the first vector, this is like 1, 2, right? The second column of A is equal to minus 1, 3, and the third column of A, this would be equal to 0, minus 6. Okay, so here we have 3 columns, and then we can also calculate the transpose of A. So what is the transpose of A here? Can I have someone from you to help me here? So for example, Adelio, what is the transpose of A? Adelio, can you? Adelio? Or maybe today we'll do it like this. We'll start from the bottom of the list. So we can start with Jessica. Jessica, what is the transpose of A, of matrix A? You can open the microphone and answer. Okay. What is the transpose of matrix A, which is 2 by 3? And I'm asking now Jessica. Jessica, so I want you to be attentive, then I can pick up Victor. Victoria? Transpose, yeah. What is the transpose of matrix A? We did it last time. Can you open the microphone? We can communicate faster probably. I don't remember. Okay, good. Wendy, what do you think, Wendy? It is, but Adelio, no, I think let's pick up Wendy, so you can check your the list of the names in the class, and we're going alphabetically backwards. Wendy? That's true, it's 3 by 2, but tell me the numbers. So what should I write here? What is the first column? What is the first column of A transpose? Come on. You can open the 1, 2. Okay, so 1, 2, this is the first column here. Here it will become the first row. That's true. And what should we write next? Okay, but I want all of you to be able to open the microphone, okay? So the others can also hear what you are saying or our discussion. So that's 2 is minus 1, 3, and we get here 0, minus 6. So this is the A transpose. Now for today, we're going to discuss about vectors and how vectors help us to understand the lines and the planes, okay? And this is the first time where in this course we're going to discuss how the spanning by several vectors, how vectors can span different spaces. Now,
Professor, sorry, I can't see the top of the board.
You cannot see. Is there anyone else who does not see? Can you see it now?
Now is better.
Now it's better. Okay. Sometimes, yeah, I think you get used to how you adjust your screen settings during the online classes. So today we're going to discuss the general principles of vectors, which is a simplification of the matrices. Now, you're electronics engineers. This is very important for you. If you understand this well, you're going to get a very good understanding when you do the electromagnetic field theory course in the second year, electromagnetic waves in the third year, and antennas again in third year. So you need to understand how a space is defined, because it will help you also when you integrate energy distribution in the proximity of an antenna. That's an example, okay? Or when you need to calculate the electric field as a derivative of the magnetic field in a coupled electromagnetic field. Sorry, electromagnetic field, yes, or electromagnetic wave. So when you compare the electronics engineering students and computer engineering students, the understanding of spaces, of planes, or how the space can bend and other concepts, for you it's much more important. So please, I just want to say that this is very important to understand this. So we start with the discussion of vectors. With vectors, first of all, I think we know what is A plus B minus C. Can I have someone answer, give me this answer? So what is A plus B minus C here? I'm going to pick, I didn't get any answer from, I can get Sebastiano. Sebastiano, what do we get here for A plus B minus C? Sebastiano? Sebastiano, can you hear me? Sebastiano, can you open the microphone? Because I don't want to bend and get close to the screen of my computer and read what you are writing. Okay, so can you please open your microphone? If you don't have access to a microphone, you can tell me it's fine, but you get 0, 12. Now this A, this vector A, this is an element of R squared, okay? Because this vector A, don't worry, okay. So this vector A, it is a subset of R squared, because this vector is defined by a pair of numbers, only two numbers, and we can find where we can allocate this specific vector. At the same time, we can also find them where they are on the Cartesian coordinate system. For example, the vector A, 1, 2, this is 1, 1, 2. Vector A, we can find it right here, okay? Then we have the vector B, which is minus 1, 3. Minus 1, 3, we have 1, 2, 3. And this vector is going to be something like this. Now, they both indicate a point in the Cartesian coordinate system, and we can add and subtract them in whichever way we want. And let's find out, for example, where is 0 minus 6. 0 minus 6, x is 0, minus 6 is 1, 2, 3, 4, 5, 6. So apparently, we're going to have this vector, which is pointing all the way down here. Now, in order to add in the same way that we did it here, we know that A plus B minus C, A plus B, this is the vector A, we add the B, but to add the B, we just move this in parallel direction and we bring this somewhere here, okay? This is the B. And from here, the B, because we know that when we add vectors, we bring, this is a vector A, this is the end of the vector, and this is the tip of the vector. And let's assume this is A. If you want to add the B, we bring the end of B to the tip of A, okay? So we do it like this, so more or less we're going to have this configuration. And then we have minus C. Now, C itself is this vector. When we do minus C, that means that we get, this is the C, okay? So the numbers, we did not pick them very correctly, but as a result, it looks like it's going to be what Sebastiano just answered us, is going to be 0, 12. Now, this is how we deal. Yes.
Why is 12 there?
Because, oh, that's a mistake. It should be 11, right?
Yes.
This is 11. That's correct. This is 11. And so this is how we deal with the vectors. And then we also know, for example, this was a plus b. We got how we find it. But if you want to calculate a minus b, we know that if we had a minus b would be this vector, and then the way that they are here, a minus b is going to be equal to this vector here. Okay. So this is how we can operate with them. We are still in R squared. And now I want to ask you one question. What is the union? Let me, I need an eraser. Okay, I'm not attacking. So, what is the union of points which can be expressed as any constant k times a, such that k is a real number? So, what can you construct if you just, k is a constant, a is this initial vector. So, any answer for this? We can assume the following: k can be equal to 0. If k is equal to 0, we get this point here, okay? If k is equal to 1, we get this point, which is 1, 2. So we get somewhere here. If k is equal to minus 1, what do we get here? We get minus 1, minus 2. So we're going to get some point down here. If k is equal to 1 over 2, we get some point here, okay? When k is equal to 2, we get here 2, 4. That's 1, 2, 1, 2, 3, 4. So it's going to be somewhere in here. So if we get a lot of points like this and you change the value of k, what do we get? What is the result? Do we always need a k? Yes, because we are asking for a linear combination of the given vectors. Okay, so k is just a number. Material. I think it's a Darius question. I have to go to. Okay, so what do we get? What is this? Reda, what do we get if we get a k times a vector?
We get the straight line.
Exactly. Okay, so the union of points like this. This is the definition of a line. Okay, good. So we get a line. Fine. Now let's ask this other question. What is the union of? What is the union of points which are k1a plus k2b? What are these points? Where k1 and k1, k2, they are real numbers. So what is the union? Now this means that imagine for a moment that k1, and let me ask also this one. Let's assume k1 is equal to k2 is equal to 0. What would be this point? This point would be the origin, okay? Or what we can do is that we can, maybe I can use a different color, or let me use a black color. So when k1 is equal to k2, we get the origin. Okay, let me make a black square. If k1 is equal to 1 and k2 is equal to 0, I think we get a black square right here, okay? If k1 is equal to 0 and k2 is equal to 1, we get this other vector, right? Because this is a linear combination, so we're getting just the A or B separately. So far, we made here also a black square. Then, imagine for a moment that we can assume that k1 is equal to 1 and k2 is equal to minus 1. What do we get in this case? Let's substitute these values. We get k1 is equal to 1. We get 1, 2 minus 1, 3. Okay, because this is what b is, and this would be equal to 2 minus 1. Okay, 2 minus 1 is going to be a point somewhere here, which we denote it like this. So we get another square. Okay. So if we move around with linear combinations with different k1 and k2s, what do you think we can construct? What is the union of all of these points? We can get again an answer from who was Reda. What do you think, Reda?
Could you repeat the question, please, one more time?
So, I'm asking if we change the values of k1 and k2 from
Yes.
minus infinity to plus infinity.
Yes.
The union of all of these points, what set are you going to define? Çfarë bashkësie do prodhoshti nëse ty ndryshon kënjë përbyshin duke shëmzuar A dhe B? What can you get? You said that you got a line when you had only A, right? You said that the union of points which are KA, it's a line. What about this other one?
It should still be a line.
Well, is it a line? You have a black point here, you have one here, one here. Is it going to be a straight line or what?
No.
So what is it? Well, you get a plane here because you can define any point in this on the whiteboard using these two vectors, okay? So the union of all of these vectors, this would be, in fact, this can be a plane. Because I can give a point here, and we can always determine, for example, let's say this point here. We randomly picked it, and it looks like if we go one unit of A, plus another unit of A, plus another unit of A, this looks like this is 3A. Okay, so we can find this point as a combination of these two. What about if I am here? What about this point here? This one, we could say that it is equal to 3A plus 0.2 times B, because B is this one. So you get a little bit of B, then you get this point, okay? Then you can also move this way. What is this point? This is 3A, because this is the vector A, minus 0.2B, so you come this way. So it looks like any point on the board we can define as a linear combination of these vectors, okay? So, so here we can say that linear combination of these two vectors of A and B, we get a plane. Now, this is regarding the linear combination of these values, and we never forget that A and B is also a subset of R squared, because B is composed by a pair of numbers. C is a subset of R squared too. But now we can also define some other vectors, such as V1, it can be equal to 1 minus 1, 0. V2, it's equal to 2, 0 minus 1. And V3, this would be equal to 3 minus 1, 4. So here we have three vectors where all of them, they belong to R squared, R cubed. So V1, we can write it like this. It belongs to r cubed, because each vector v3 is composed of 3 numbers. Okay, so we need a triplet of numbers to determine a point in space. And a point in space, at least for the two-dimensional case, we used the Cartesian coordinate system. Cartesian coordinate system. And then we can say that any linear combination, so if we do something similar, let's check what is the union of a union of K1 V1, okay, plus K2 V2. So what is this? Could this be a line or a plane? Which one would you rather think that you can construct? So let's ask Medina, that is next in line. Medina, what do you think? Okay.
I don't know.
Okay, so let's try to figure it out. Before a moment, we said that if we get the union of K1A plus K2B, we can construct a plane, okay? Një plan, pra një hapësirë dy-dimensionale. Çdo pikë aty mund të përshkruhet në këto dy vektorë. Në mënyrë të ngjashme, edhe kjo pika këtu 1 minus 1 0 dhe 2 0 minus 1, këto vektorë mund të përkufizojnë përsëri një plan, sepse kemi dy vektorë të cilat mund të përshkruajnë një bashkësi dy-dimensionale, okay? Dhe njëkohësisht pastaj ne mund të we can also assume the union of K1 V1 plus K2 V2 plus K3 V3, which in this case this would be the complete space, because this is similar to the way that we can describe the three-dimensional space or the volume in your rooms that you are right now. You can describe any point in this room by x, y, and z. Okay. Traditionally, we assume that x, y, z, they are Cartesian coordinate systems where all the coordinates, they are 90 degrees with respect to each other. So they are orthogonal, or they are conjugate, or they are perpendicular. It is a very good choice, but the same task which is fulfilled by the Cartesian coordinate system can be done also by any random choice of these vectors. Okay, so we can say that this linear combination, where we have only two vectors, we're going to have a plane which is two-dimensional plane. Okay, whenever we have three vectors like this can define the whole space, or we can call this 3D. Okay, or the complete volume of the room in your where you are sitting right now. Now, let's think for a moment another question. And I can ask also for some help after Medina. I can ask for help from Marcelo. So Marcelo, if you follow me carefully, I want to ask you the following question. So, what could be the union of these vectors? We have 1, minus 1, 0. So this one, we already have it, right? It's on the board. The second vector is 2, 0, minus 1. 2, 0, minus 1. And the third vector will be equal to 3, minus 1, minus 1. So, using these three vectors, what space can you scan or can you span? Marcelo, can you have a look at? Can you hear again to my question? So the question is, having these three vectors, let's call this one V1, V2, and V4. We call this V4 because V3 is already somewhere here. So in this case, what is the linear combination of these three vectors? Can we describe a space? Sorry, can we describe a plane, which is two-dimensional plane? Or can we describe a three-dimensional space? Marcelo? Marcelo, are you present? After Marcelo, who can answer this one? Anyone in the class?
I think it is a three-dimensional space.
That's a good try. Why do you think so, Isabora?
Because the last time we said about the three vectors and the combination, the union of them was space.
Yeah.
So this is space too.
Okay, but let's have a look closely. This is K1V1 plus K2V2 plus K4V4. Okay, so this is this can be the definition of where to find some points. Okay, but then for a moment, let's have a close look. Do you see, Isabora? Do you see any similarity between V1, V2, and V4? Do you see any relationship?
V1 plus V2 is V4.
Exactly. V1 plus V2 is equal to V4. That's true. So if this is the case, I think I can write it the same way like this, right? So if we do it like this, we can really see that this linear combination of these three vectors, which are written here on the board, they are in fact a linear combination of only V1 and V2. So V4, this is described already by V1 and V2. So V4, we can call this one useless. Okay? This is useless or redundant. So redundant, this is telling us nothing new. So we already had V1 and V2, which means that in this case, the possibility of these three vectors to span the three-dimensional space, it was there, but since V4 can be described as a function of these two, we can say that this one, it does not describe the 3D, but it describes only a plane, a two-dimensional structure. So here, we can simply write that this is still 2D. But this one, this was 3D, because here, V1, V2, and V3, they are linearly independent of each other. But more details on this, we're going to study in a few weeks. Okay? This is not the complete end of the story, but for now, we need to understand that if we have a two-dimensional space, a plane, you pick up a piece of paper, okay? You have a piece of paper, and how many dimensions is this? That's one question. At least using Cartesian coordinate system. You say it's 2. Why? Because you can draw a vector here, I'm just drawing here, and you can draw also another vector here. So these two vectors are enough to describe this point, this point, this point, and any point here. At the same time, we can also use these vectors in black, this and this, okay? So the pair in black or the pair in red, as long as they are here, they can still describe any points on this piece of paper I'm holding here. At the same time, we can have even these vectors here at the bottom. This is also a possible pair. So it looks like we can define an infinite number of pairs of vectors, but we need 2, that's for sure. That's a constraint in order to span this space. That's good. Now, I can ask you this will be very important for you. How many vectors do I need to describe the outer space of this cylinder? You get a Coca-Cola can, and it's a space again. How many coordinate systems do we need for this? We still need 2. It's two-dimensional space. We need one angle change, which is going to be this way, and one description like this. You are going to learn in detail these, because you need to know these when you go to the second year. So this is a surface area. This is also two-dimensional. You don't need a third coordinate. So keep in mind, so we're trying to remind ourselves on these important aspects. Isabora, is it clear? Okay.
Yes.
Thank you for your answer, for your voluntary answer. So now that we have these vectors, or this little understanding of how they can span a specific space, and in principle, we can say that, for example, I erase this here, but technically, we will say the following. We will say the following. The vector 1, 2, and vector -1, 3, they span the board, okay? Or they span a plane. Because spanning means that linear combinations of these two vectors can go to any point on this whiteboard. Okay, so anything you draw here on the board, these two, you can find this point, this, and everything that is here. But we'll never describe a point which is 1 meter away from the whiteboard. Okay, for that one, we need a third vector which should not be on the plane. Okay, to cover the three-dimensional space. Good. Now we're going to move forward with a series of definitions which will be very essential. And the first definition that we have to provide is the inner product. Okay? Inner product is the product between two vectors in principle. So far, you know how to multiply matrices, right? We know this one, it's a very easy task. And I'm going to ask my next help from Borovsky. Ljum, I want you to be a little active. So
yeah,
imagine
okay.
that we have a matrix 2 by 3. Can we multiply this one with a matrix with its A transpose? Can we multiply this with A transpose?
I believe we can, because the column of A equals the rows of the transpose of A.
Okay, that's good. So what is the result here then? It's a matrix of what dimensions?
It's a matrix of, if I remember correctly, wait. It should be
It should be
2 by 2, I believe, or
yeah, that's right.
yeah.
This is so the inner dimensions. They are the parameters that will multiply each other subsequently. But the dimension, the result of the product is going to be a matrix which is 2 by 2. So we check for the equality of the lines for the black line here, and then the dimensions will be the one in red. What about these two vectors? 1, 2. Can we multiply this with the vector 1, 3?
Do I answer again?
Yeah, you answer this one. First of all, what is the dimension of this vector, 1, 2?
It's 2 by 1.
What is this other vector?
Again, 2 by 1, but you can't multiply because the column of the first is not equal to the rows of the second. Not defined.
So this is not defined, okay? So we cannot define this multiplication. But what we can do is that we can get the transpose of this one. We can write this one as 1, 2, and we multiply with -1, 3. And the answer here was, so what is the dimension of 1, 2?
It's 1 by 2.
That's correct. So we have one row and two columns. And the other one is 2 by 1. So what will be the dimension of the product of these two vectors?
1 by 1.
That's true. So you get just a number. If you get anything which is 1 by 1, we call this a scalar. And the result here is going to be 1 times -1 plus 2 times 3. Okay, so this is how we multiply those. We go like this. And we do pairwise, we pair the numbers 2 by 2. And what do we get here? We get -1 plus 6, we get 5. So this is the definition. So let me use this part of the board. This is the definition of the inner product. Okay, the first thing we're going to learn today. Inner, not the first thing, but this is the inner product between two vectors, and this is defined as A times B. Okay, if these are vectors. So A times B, this is a definition like A times B. This is inner product. This would be equal to A transpose times B. Now, this is it. Next, we're going to discuss about the magnitude of a vector. But now let's give a couple of examples here. So here, the inner product of A times B, in this case, I think we solved this one. This would be equal to 5. And this inner product, this is also called dot product or scalar product. So we can call this one dot product or scalar. We call this scalar product because the result is going to be a scalar quantity which just describes scale, does not include the direction. Vectors have both magnitude and direction, but this one, it just gives a number. For example, the work you're going to study in physics, the work is equal to force times distance. This is a dot product. These two are both vectors, and this is going to be equal actually the magnitude of F times the magnitude of D times cosine theta, okay? So there is also a cosine theta there. So vector, this is a dot product or scalar product, okay? And this is a scalar quantity, it's just a number. So the electricity bill that you pay at the end of each month, it's shown in kilowatt hour or joules. And these joules, they don't have any direction, it's just a number out there, okay? Now, so this is the inner product between any two vectors. We can also define the inner product between, let's say, the vectors 1, minus 1, 3, and another vector can be 5, 2, minus 1. So what is the inner product between these? We take the transpose of the first one, which would be this, 1, minus 1, 3. We multiply it with 5, 2, minus 1, and as a result, we get here 5, minus 2, minus 3, 5, minus 2, minus 3. Is this correct? Is this really true? Let me check. 5, minus 2, minus 3, we get 0, okay? So we got 0, we randomly picked up these numbers actually, but we find out that we get a 0. What could this mean? This means that these two vectors are perpendicular to each other, so they are normal to each other. Okay, we randomly picked them up, but okay, it was a coincidence. But it's good that this came out this way because maybe this means that. So let's write this. This is the vector. Let's call this one v1, and let this be a vector v2. Here, this will be equal to the magnitude of v1 times the magnitude of v2 times the cosine of the angle. Now, magnitude of v1, this can never be 0, okay, because it's a vector. And let me ask you one question. So, Lindo, Lido, what do you understand when you say magnitude? Ce përfshirë çfarë është magnitude?
Madhësia.
Madhësia, është drejt. Pra është ose gjatësia e vektorit. Pra vektori ka drejtim, një vektor mund të ketë drejtim, por mund ka dhe gjatësinë e këtij lapsit. Pra, kjo është madhësia. Dhe këtu për shembull, the magnitude of this vector v1 is different from 0. The magnitude of this vector here is also different from 0. But cosine can be equal to 0. So for what angle is the cosine equal to 0?
90 degrees.
90 degrees, okay, that's true. So we get here a 90 degree, and then, so we got this much. But now let's define how we find the magnitude of a vector. The magnitude of a vector, like similar to this definition here, it is related to the magnitude, we denote it like this. Magnitude of A is equal to the inner product, square root of the inner product of A. Okay, so this is the magnitude. We can write it here. We say the magnitude of A, this is equal to the square root of this. So in this case, what is the magnitude of V1, which is shown here? The magnitude of V1 is going to be 1 minus 1, 3 times the vector itself, 1 minus 1, 3, square root. Okay? And then what we find here, we see that 1 times 1, this is 1, plus 1, 2, plus 9, 11. So this is the magnitude of the vector v1, 11. Now, what is the magnitude of the second vector, of v2? Let's see this one. What is the magnitude of this? Sorry, I think I cannot read. So what can be the magnitude of the second vector?
The 25 plus
Yes.
4 minus 1.
Plus 1. We get the square root of 30, okay, that's the magnitude. Now that we know the definition of the magnitude, we can define, thank you, Gabriel, we can define the unit vectors, okay? So we can define a unit vector, and this is it's useful because often we may want to do the normalization of a specific data set, okay? Now, normalization of a specific data set, this is very important because often we need to compare vectors, okay? So I'll try to provide an example here, which, let me say this. So let's say you construct a vector, which initially this might include, if you remember in the first week, we said that we can construct a vector where the first value can be 1, which would be the level of difficulty of this class, right? The second variable, it was your expected grade, and the third variable can be the final grade that you are going to get at the end of the semester. But at the same time, we can also include the English scores, okay? So let's say that you expected that this class is easy, you expected to get a grade of 90, and at the end of the semester, you got also a 90. But then, in order to distinguish different students from each other, we can also associate the grade of English. So let's assume that you get to TOEFL, and the English exam of TOEFL assigns you a grade of from 0 to 1. So you might get a 0.7, okay? So you get a 0.7, so now you have a vector, but you have to merge two vectors, okay? So this is feature vector 1. Feature vector 1. Then the English grade, we just merge it here, and we put a 0.7, okay? So this is some new information. And then you can also get another grade, which could be like German score. The German-English score, you merge another data to give more details. So let's say in German, you got 0.5, okay? Now here we have, this was feature, this is, to je nota te gjuvetuja, 0.705. Ky është vektori I vogël, we merge them together. The point is that we see it at this vector, and it has a magnitude of around 10 to the power 2. But it has a magnitude of 10 to the power 0. So when we merge two vectors, which are very much different, this will be like a noise. This will be a very small fluctuation. It might not affect too much here. This is one example that you should start thinking from now, and when you go to the more advanced courses, you will understand this aspect better. Another example is the following. Imagine you have a vector which is 1, 0. You have a vector which is 1, 1. You have a vector which is 99, 105. And then you have also 2003 and 3000. Okay? So here we have some vectors, and the question is, we want to compare them. Okay? So how would we compare them? In order to compare several vectors, we often do normalization. So let's have this one here. To compare these, we normalize them. To normalize them, this means defining unit vector. Okay? Why do we do this? Because we want to see the similarity between two vectors. We often try to distinguish like this. These two vectors, if the angle between these two vectors is small, we say that they are very similar. If between two vectors the difference is larger, we say that they are kind of different. So this is how we try to visualize this. Or, at the same time, imagine for a moment that you have one vector which is pointing like this, one vector here, you can have a vector here, you can have a few vectors around here, and we want to compare these, and we can have also another vector that looks like this, and another vector which looks like this. Now, in order to compare these, what we can do is that we can try to normalize all to 1, which means that we draw a circle here with a radius 1, and we normalize all these vectors which have different magnitudes, we bring them up to here. Okay, so we define a unit vector, and unit vector, it means that the magnitude is 1. This is unit vector, and we can define one unit vector along the A it is defined as this vector itself divided by the magnitude of A. So this is the definition. And regarding this, I can ask you the following. What is the magnitude of... Okay, we know those magnitudes here. But as a reminder, here is this one here. So to keep up with the previous argument, initial vector, this is 10 to the power 0. This is also 10 to the power 0. This is 10 to the power 2. And this is 10 to the power 3. We are talking just about the magnitude. And as a fast reminder, is, for example, let's try to find what is the magnitude of this vector 1, 1. How do we do it? We say this is the square root of 1, 1. We take the transpose, okay, multiplied by the vector itself 1, 1, and this would be equal to square root of 2, which is equal to 1.4, okay? But 1.4 is around 10 to the power 0, because we try to compare different quantities by looking at the what is the order. And from here to here, we observe that we have 3 orders of magnitude difference between the first vector shown there and the 4th vector. So next, as we said, we try to define vectors or a unit vector. Then, once a lot of vectors they are normalized, we start to compare them. Sometimes in the analysis of large data sets, what happens is that we have a vector, a feature vector that describes something, and then we normalize it one. After we normalize it, we need to merge another vector, another feature vector, which is also a normalized vector, which means it has magnitude 1. Once we merge them together, you're going to hear this in the future. Once you merge 2 vectors, the magnitude is not unity anymore, is not 1 anymore. So what you do is that you normalize it again, okay? So you have a different space. When you say space, you have two dimensions, then you go to 3-dimensional space, whatever. And then you normalize it again, because this is the only way to compare these data sets, okay? Because merging these little numbers to this huge vector might not exhibit all the different, all the possible differences that come from one feature or another. Now, we define all of these, and let's see an example. For example, let's try to find a unit vector which is along the vector 1, 1. So the unit vector here is going to be equal to 1 over the magnitude, okay, times the vector itself. The vector is 1, 1. The magnitude is 1 over square root of 2. So here we are, 1 over square root of 2 of 1, 1. And once we have this, we know that any constant multiplying a number or a matrix, we multiply them one by one. So this is going to be 1 divided by the square root of 2, and 1 divided by the square root of 2. So the magnitude of this is 1 now, or this is something like 0.7, 0.7. So this is a normalized version of this initial vector here. Okay, so these are some important definitions which we need to know when we discuss these aspects. Another topic that we want to discuss, and meanwhile, if you have any questions, please interrupt me, okay? Okay, so we were talking before a while. Probably we can take these away, but let's keep them for another moment. We can delete these parts. But let's assume for a moment, we said that one line, it can be defined by a single vector. Okay, we wrote it on the board. We said if you have a vector A, so let's say you have a vector like this. What can we do with this vector? With this vector, we can define this point. If you multiply this vector by 0.7, we define also this point. If you multiply, let me make the tip a little more clear. If you multiply this vector by 2, we also define this point, by 3, this, by -1, this, and it looks like we can define all the possible points, okay? So a line, we can simply state that the line L1, this can be written as a constant CT, okay? So this is a line, and also we can define another line which can be written like this, P plus CT. Now, so once we look at these, the first question that we can ask is the following. If we have the line L1 and L2, does the line L1 include the origin? And the origin, it is 0, 0. Here, C is a constant, and it can be any real number. So I think we asked, we can ask Ledio. Ledio, do you think that line L1 includes the origin?
Yes.
Why?
Because it's like a function y equals a times x.
That's true. Exactly. So this like that, and also this C can be 0. It's a real number, right? We're not saying that. We could also say this. We could say the C is a real number excluding the 0. Okay, we don't see this. So yes, the 0, 0, 0. If it is two-dimensional space, it is a point of L1. So we can say this. What about for L2?
Well, if p is not 0, then no.
That's true. Okay, so if p is not 0, then no. So when we define lines in the Cartesian coordinate system using the principles of vectors, it is easy. Okay, we're going to solve a couple of examples. You'll feel good about it. I hope you'll understand them. But this one does not include the origin. Okay. Similarly, we can define a plane P1, which is going to be equal to C1t. This is a vector, plus C2v, or we can also have another plane P2, which is going to be equal to P plus C1t plus C2v. In principle, we need two vectors to define a plane, and this is, but again, we can ask the same question. We can say, does this plane pass through the origin? We could say yes, because C1 and C2 can both be 0, it's fine, but P2 does not always pass through the origin, because this initial plane, which would be like P1, is just shifted up by another vector. So how can we imagine a plane passing through the origin, you might assume here we have x, y, z, and you can have a plane which is looking like this, and maybe it's passing through the origin. But at the same time, you can have a different plane which is way above the origin. This does not intersect it. So the one in red can be P2, and the one in black can be P1. Now, regarding these aspects, let's try to see if we can pick up an example. Okay, so let's think for a moment. Let's assume we have a point which is -1, 1, -1, 1, which is this vector here, and we have another vector which is 3, 2. So this vector which is 3, 2, the question is, so let's write this here, we have -1, 1, and 3, 2. The question is, find a line which passes through these 2 points, okay, here and here. So find the line, find L1, okay, so let's do it like this. So how can we determine a line which is passing between these 2 points? Now, it looks like, if we look at this expression here, these 2 line expressions here, it looks like the most important thing is to determine a vector which is pointing in this direction, okay? So if we try to draw this line to the best of our ability, this looks like something which is going to be like this, okay? And we are looking for any vector that would look like this, or like this. We try to draw this one in red. So let's make this a little better. So the question is, how can we find this vector which is going to point this way or exactly the opposite way? How can we find that direction using these values? Any idea? Let's ask here Christy Xiao. So how can we determine this? What if we do, let's just say that this is
maybe we can multiply the 2 vectors.
Okay, keep this in mind. Let's say, for example, this is point P, and point Q, this is equal to, what was this, 3, 2, right? So if we multiply them, well, if we multiply them, then maybe we can get the inner product of these 2 vectors, okay? If we multiply them, we'll just get a number. We don't get a direction, at least if we multiply these 2. But let's think for a moment, let's assume, so I'm drawing the same vectors which are shown here. There is this vector here, okay, and this vector here. Imagine for a moment if we take the negative of this one, so this shorter vector. What is the negative of this shorter vector? Is this one, right? So now this is minus P, this one in black is minus P, right? This one in red, this is vector Q. Would you agree? Now, if we add this black vector with this white vector, what do we get? So we get this vector, which is equal to minus P plus Q. Right? Because this is how we add vectors. We have this vector, we add this, we add this, we add this. Pra ne kushtojmë vektorën, çfarë bëjmë? Fundin e një vektori e vendosim te maja e vektorit të mëparshëm. Dhe kështu bëjmë me radhë, bëjmë seri. Pra këtu, Kristi kishte fjalën se harrojmë po. O Kristi, pra a jeni dakord me këtë? Pra, kjo me të kuqe ishte vektori P, me të zezë P minus P, kjo pastaj ishte Q, a jeni dakord që po të marrim të vektorin e zi këtu me këtë vektorin e kuq, a jeni dakord që del ky vektori këtu? A Kristin?
Po, ai vektori del.
Okej, në rregull. Pra i bie që një gjë që mund të bëjmë thjesht minus P plus Q dhe këtu na japi një vektor që ka këtë drejtim. Dhe po ta bëjmë këtë, i bie që minus P plus Q na del të minus 1/1 plus 3/2 dhe kjo do të dalë pastaj 4/1. Okay, so we have a vector which is form 1, which describes, let's say, this line. But this is just a slope. Now I can ask you also this one. What is the slope of this line? Sa është tërësia?
Katër apo jo?
Let's think about this one. So this line is shown here. Tërësia, let's write this one here for a moment. We know that the slope është barabartë në tangjentën e këndit, teta, ku këndi teta është këtu, dhe kjo është barabartë në delta epsilon përmbi delta x. Okay, so this is how we calculate the slope. So in this case, we need to know what is this delta y here, okay, divided by this delta x here, which means that this vector was here, this is 2, this is 1. So in this case, we have to calculate what is this side, Sasha. Kristin? Mos harroni që ky vektori ishte të njëshit, kjo është minus 1/1, kjo është 3/2. Pastaj sa vjet kjo? Delta y is equal to 2 minus 1. Okay, and here, delta x, Christy, can you evaluate this one? What is delta x? Because we are looking at this side here, at this triangle, and we want to find the tangent of this angle theta. So this delta x is equal to 3 minus 1, so it's 4. So the slope, which we try to repeat it here, this is going to be equal to 1/4. Okay? So this is going to be the slope. But now, is it clear so far, like I said?
Yes, it's clear.
Okay, so now the thing is that the complete equation, and another question it comes again to our mind is that, does this line pass through the origin? When we look at this, it looks almost clear that this is a straight line. This is not passing through the origin. So this line, it should be expressed in this, so pick this. It's going to be an expression like this, like L2. So we need to determine what is this vector P. Now to determine this vector P, we can select any reference point. Okay, so we can pick here 1 minus 1. So L2, we can write this one as minus 1, 1 plus C times 4, 1. Okay, so this is the, let's say, this is the equation of this line, which is looking like this. And this vector, which shifts the whole line from the origin, in this case, we just pick any point which was on the line. Okay. So this was okay. Then I think it's good if we do any example of this nature. Okay, where we look for the equations of the planes, and for this, I think we can. Okay. Let's assume that we have a plane which can be expressed as SD let's do it like this, SD plus Okay, so let's assume that this is a plane. First of all, we just look at it, actually, is it really a plane? In order to have a plane, we need to have at least like two different directions, which in this case, we have them because we have two vectors. These two vectors are different from each other, which means that we're not at least in a line, we're not in 1D, as we've explained before this. So here, the first question is, let's find the Cartesian representation of the plane. So this is a plane. So what is the Cartesian representation of the plane? Now, how do we express the equation of a line in Cartesian coordinates? The equation of a line in Cartesian coordinates, we can express it like this. Y is equal to mx plus b. Okay, this is the equation of a line. The equation of a plane, so let's write it here. This is the line. The equation of the plane is equal to anything that looks like this. Z is equal to ax plus by plus d. Okay, where a, b, d, they are constant, x, y, z are the coordinates. This is ax, so this is the plane. So we are looking for an expression which looks like this to some degree. Now, what this means that here, so this x, y, z, which are expressed by these two directions, we need to recombine them and have an expression which is composed only of x, y, z and some constants. So we are looking for this type of equation, okay? For this equation which is here in red. To do it...
sorry, Professor, can you just tilt the camera upwards a little? I can't see the numbers.
Oh, okay. I thought...
Very well.
Sure. Thanks for the note. Okay, this is better?
Yeah, it's okay now. Thank you.
That's good. Okay, so what we do here is that we just write that x is equal to s plus d. Okay, the y, this is equal to 2s plus 2t. Is it correct? Yes. I think 2s plus, wait a second, this is minus 2. Oh, I written the same vector twice. Okay, sorry, that's a mistake. This was not intentional, but in fact, if this was the case, this would mean that we don't have a plane, we would have a line. But similarly, this is my mistake, the same thing, so that was a line actually, okay? That was a line, and when it comes to this, what can you say about this? Do we have a plane now? I changed the numbers, because I had written the same vector twice. Is this equation of a plane now? This is my question.
Yes, now it's a plane.
No, it is not. Because the second vector, it is the same as the first vector. okay? Because the second one is just the first one times 2. So this is still a line, so this is not correct. Or it's not correct, it's not a plane. Why is this the case? Because let's imagine for a moment that we have a vector which is shown here like this. Let this be vector A, okay? And then the second vector, let it be another vector which is 2A. 2A. Can these two vectors span a plane? Can we describe any point on the board using these two vectors? No, because they can define a line, okay? So any linear combination that looks like, or let this be B is equal to 2A. So C1 times A, where A is a vector, plus C2 times B, where B is another vector. What is this? Is this really a plane? Let's check. We can write the C1 times A plus C2 times B, but B is equal to 2A, right? So we can write it like this, 2A. And this would be equal to C1 plus 2C2 times A, right? So we see that this is just a constant times A. So this is a line. Is it clear? So we don't pick two vectors which are parallel to each other to define a plane. But if we have a vector which changes very slightly from B, if this is this one, and this one in red is C, then A and C can span a plane. So again, here we still don't have a plane because this vector is twice the first one. So they are just pointing in the same direction. We should have at least two different directions to obtain a plane. So I have to erase this again. Be careful when we write these, but my first mistake, it was really unintentional. This is minus 217. Minus 217. So when we come to these equations, let's rewrite these again, just to correct also some of our mistakes. Let's take this out. A few minutes ago, we even did an example where we gave three vectors, and three vectors did not span the three-dimensional space because the third one was a function of the first two. Okay, so we should have completely different expressions. So let's see here: x is equal to s minus 2t, y is equal to 2s plus t, and z is equal to minus s plus 17. Okay, so here we have all the points which are described, which they should be in a plane, as we argued. And now the question is, we have to remove the constants s and s. In order to do this, from the first expression, we can find that s is equal to x plus 2t. Then, from the second equation, we can get that y is equal to 2 times s. What is s here? We get it from the first expression, so this is x plus 2t plus t. And then from here, then finally we can say that z, this is equal to minus s, and minus s is minus x minus 2t plus 7t, and this would be equal to minus x plus 5t. Okay, and what we have not done yet is that we can describe here the t as a function of x and y. Okay, so from this expression, we can, if we look at it carefully, we can find that t is, we get here y is equal to 2x plus 4t plus t. So this is equal to 2x plus 5t. And t is equal to y minus 2x divided by 5, right? So in here, we're going to get minus x plus 5 times y minus 2x divided by 5. what do we get here? We get minus 3x plus y. Okay, so if we look at the last expression here, we get that z minus 3x plus y is equal to what? Is equal to 0. Or, no, this was a mistake. Okay, if we, well, if we write it like this, it's going to be plus, y is going to be minus 1. Maybe it is even best. Okay, so let me write this. From there we get z is equal to minus 3x plus y, or we can have here 3x minus y plus z. This is equal to 0. So we get this expression, and this is very much similar to this, okay? So there is, so in order to understand spaces, what did we say? We say that we need at least two vectors which are linearly independent, which means that they are not parallel. We can construct a plane. In this representation, this is a plane. Now, in the Cartesian coordinate system, we need, let me think for a moment. A plane is uniquely identified by a vector that is perpendicular to the surface plane. Before a few minutes, I was showing you, on a piece of paper like this, we were saying that this pair of vectors which are in red, they span this white paper, right? Whichever the angle of the paper is. This pair of vectors here in black, they also span the whole paper. And these also, this little pair of black, they also span the whole paper. But, so there is an infinite number of pairs of vectors that can define this, right? But we need only one. To do it, we can define this, okay? This is a vector which is perpendicular to this plane everywhere, okay? So unique identification of a surface area, we need a normal vector. And with normal vector, we can, for example, we can ask the following question. How many surface areas does a sphere have? Who can answer this? Anyone in the class can give it a try. So the sphere, how many surface areas does it have? How many sides? Anka. Or a cube. How many surface area does a cube have? How do we count them? We look at the vectors perpendicular to these sides, right? So we have one in the front, on the back, up, down, left, right. So this has 6 sides, right? Why? Because this has 6 different vectors which are perpendicular to the sides. Then, let me ask you this, a cylinder. How many sides does this have?
2.
Why?
Oh, let's say it's just one vector perpendicular and one vector perpendicular to the side.
What about this outer surface which is curved like this? Can you construct a perpendicular vector also here?
Yes.
Yes, that's correct. So probably this has 3 sides. Three surface areas. Or okay, let me call this, because now we might be confused, but to make things more clear, we call it 3 surface areas. Okay, why? How can we clearly define that there are this much? Because in cylindrical coordinate system, you can define a vector which is unique, because in cylindrical coordinate system, we have these coordinates. We have r, phi, and z. So if we have this area, we can define a vector r, which is perpendicular from the center, which is pointing perpendicular to this surface area everywhere. Okay, so this makes it a single surface. So that's what we are trying to say, is that also in here we can read the normal vector to this plane by looking at the coefficients of x, y, and z. So this normal vector at this point, this is n. This vector is the vector which is 3, minus 1, 1. Okay? This is the normal component to this plane that we wrote here at the top of the board. And now, what we can also say, we can say that this equation, we can describe this equation by nx. This is equal to 0. Okay? These two expressions are equivalent. Okay? This expression is equivalent to this because if this is n and x is the position vector, which is equal to x, y, z, right? This is the normal vector to the plane. This is x, y, z, the position. This is the inner product. The inner product, how do we do the inner product? We take the transpose of this n, which is here 3 minus 1, 1. Probably, I don't need to show this, and this is x, y, z. And if you take the inner product between these two, this is what we get, right? We get this expression here. Okay? Now, one thing that I can ask you is the following. If this is vector, let's write it like this, S times V, okay, plus T times W, where V is the first direction and W is the second one. What could you expect to find from NV? So we want to find the inner product between the N and the V. Let's calculate it. Let's calculate it and see what we get for this inner product. So who can do this? I mean, anyone that is as a volunteer? So this is the transpose of N. What is V? Anyway, I need to pick someone. So after Christy, I think Joanna. Joanna, can you answer this? So V, it's 1, 2 minus 1, 1, 2 minus 1. What is the answer here? We get here 3 minus 2 minus 1. What do we get? 0. What do we have if we take the inner product of, no, how did I write this one? I said V, I call this W. Okay, that's right. So what would you expect? Joanna, can you answer? Or maybe you're just writing on the comment section. Okay, no answer. After Joanna, we have Isabora. Isabora, any opinion?
What was the question again?
The question is this. What is the inner product N with W? Well, we're going to find
I can see the W.
W is right here. It's
Oh, okay.
because
Then the product is the transposal of N.
which is 3 minus 1, 2, right?
Yes, and the W minus 2, 1, 7.
Okay. What is the
Then we have minus 6, minus 1. That is a 2, right? So plus 14.
Wait a second. We have a mistake here. We have a mistake. This is, sorry. This is 3 minus 1, 1. I made a mistake. The normal vector is 3 minus 1, 1 because we get it from here, right? I think this is also clearly classified here. So this is minus 1.
7.
What do we
Plus
get?
7, sorry.
So, do you have any idea why we get here 0? Why the inner product of N with V and N with W is equal to 0?
Maybe they're perpendicular to each other.
But would you expect this before you calculate it?
Yes, because we said that we use one vector who is perpendicular to the other vectors.
Okay, we said this one because I'm showing again this piece of paper because now we are used to looking at it. So the vectors which define this surface area at any orientation, it's a pair which is lying on this piece of paper. The normal vector is this, which is the angle is 90 degree with any vector which is lying on this plane. So always the normal times any vector, including those two, the dot product will always be 0 because the angle is 90 degree. Okay, so this is also expected to some degree that this inner product would result into being a clear 0. Now, do you have any question?
So the equation we use at 3x minus y plus z equals to 0.
Yes.
It represents the whole plane?
Yes, it does.
Okay. So the vector n represents the plane. Okay.
The vector n is the normal vector to the plane and is the only unique description or representation for the whole plane. Yes. Okay. Any question then further to this discussion? Okay. If you have no question, we can